Everyone, welcome to our first lesson in 2020 summer session. This is our first lesson. Some of you may have learned this in Math 10. I don't know. Some teachers might teach it in Math 10. I certainly did. For some of you, this might be a review, but this could be new for you as well. So let's just go over these together. So today, the lesson is about converting between mixed radicals and entire radicals. And we'll go through them and we'll talk more about radicals. There are two different methods that we're going to use. One is by using the perfect powers, and the other one is by prime factors, okay? So let's take a look at radicals here. So let's find some patterns, okay? So we have four expressions here, I guess. We can simplify here. We have square root of 4 times 9. Now we know 4 times 9 is 36, so this really is the same thing as square root of 36. And hopefully, you should know by now that square root of 36 is simply just 6, right? Because 6 squared is 36, okay? Now, if you look at the second one here, so what we did, or what I did was I split the 4 and 9 and then make it into two radicals instead. So let's see if it's going to yield us the same result, okay? So we have the square root of 4 times the square root of 9. Now we know square root of 4 is 2. We know square root of 9 is 3, and 2 times 3 is indeed 6. Okay, so, based on this one single example, it seems like they are the same, okay? What if we try a cube root? Okay, would that give us the same result? Okay, so let's take a look. So we have the cube root of 8 times 125. 8 times 125 is 1000. Okay, so we have then the cube root of 1000. And you may know, you might not, doesn't matter. The cube root of 1000 is equal to 10. Okay, so cube root of 1000 is equal to 10 because 10 times 10 times 10 is equal to 1000. Okay, that's why cube root of 1000 is 10. All right, so same thing, we're going to do the same. We're going to split them, and then we're going to see if it's going to work, right? So the cube root of 8 is 2. Cube root of 125 is 5. So 2 times 5 is 10. So indeed, this also works, okay? So the rule of thumb here, or the generalization that we can make here, is that when we have product inside a radical, what we can do is we can actually take them outside of the radicals and split them, right? So instead of one single radical, we can actually make it into product of two radicals. Okay, so you can see here, the nth root of a times b is the same thing as the nth root of a times nth root of b. Okay, n could be any number, right? So it could be 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Nth root, obviously, cannot be negatives, okay? And we can use this property to simplify square roots and cube roots that are not perfect squares or perfect cubes as well. Okay, but then what that means is we will then have something remaining inside the radical. Okay, so I'll show you what I mean by that. So here are three examples. Square root of 99. So we are going to first using perfect powers. So the perfect powers are 2 squares. So 4, 3 squares, 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Usually that's pretty much all the numbers you need to use. I mean, it could get bigger, right? So it could be 121, 144, and so on. Okay, so what we're going to do is we're going to look at this number. This is what we call a radicand. Okay, we're going to look at a radicand. Maybe I should do a quick definition just in case you have not heard of it before. This x is what we call a radicand, and this n is called the index, and the whole thing is called a radical. Okay, that's the whole thing. Okay, so we have a radicand of 99, and what we're going to do is we're going to look at these powers, okay, these perfect powers, and we're going to find a factor of 99. Okay, which one of these perfect power is a factor of 99? I think we can see 9 is definitely, sometimes there could be more than 1 though, okay? Sometimes there could be more than 1, so you always look for the biggest possible, okay? So 9 is definitely a factor, and I do believe it's the biggest factor. So what I'm going to do is I'm going to change square root of 99 into 9 times 11, because 9 times 11 is 99. Now, from the multiplication properties of radicals, then we can simplify this by splitting the radicals. So this becomes root 9 times root 11. We know that root 9 is 3, and there's absolutely nothing we can do about root 11, so we just leave it as it is. So then the final answer to simplify this radical is 3 root 11. Okay. Second example, root 72. So this one is the one I mentioned earlier. And we actually have more than one factors here among these perfect powers. 9 is definitely a perfect power or a factor of 72, but we could do better. Okay, 36 is also a factor, and it's actually bigger than 9. So in this case, we're going to use 36. Okay, so then 72 is the same thing as 36 times 2. Okay. And well, again, we can break this into two radicals. So root 36 times root 2, and we know root 36 is a 6, so this is simply 6 root 2, and that's it. Okay. Okay, so the third example, we're going to move away from square roots. Here we're looking at cube roots. Okay, so we do something similar, except we don't look at perfect squares anymore, right? We look for the perfect cubes as the factor. So instead of this list, because this is only perfect square, we look at the perfect cubes. So 2 cube is 8, 3 cube is 27, 4 cube is 64, 5 cube is 125, and there's there's more, but for this example, there's no need to continue because, 125 is already bigger than 72, so it cannot be a factor already, right? So we are looking at 8, 27, and 64. Which one of those three is a factor of 72? 8 is definitely a factor. So we can split this into the cube root of 8 times 9. Okay, so then again, we can split this into the cube root of 8 times the cube root of 9. We do know that cube root of 8 is 2. And there's nothing we can do about the cube root of 9, so then we just leave it as it is. So the final answer is 2 times cube root of 9. Okay, hopefully that makes sense to you. There are 3 examples for you to practice. You should pause the video and give it a try. Okay, so I'm assuming that you finished it. I'm going to quickly go over these 3 here. I'm not going to spend too much time on it. But I'll show you the answers. So 32 is equal to 16 times 2. Okay, you could use 4 times 8, but you'll realize that it's not the biggest power or biggest factor. You know what? I'm going to do that. Okay, I'll show you. It could actually work as well, but it's going to take one extra step. So 4 times 8. We know we can split this, so then this is going to be square root of 4, which is 2, times the square root of 8. However, 8 can be broken into 2 different factors, right? 8 is the same thing as 4 times 2. So then we can split this into 2 times square root of 4 times 2. Okay, now we know square root of 4 is a 2. So again, we would then end up with 2 times 2 root 2, right? This 2 came from there. This 2 came from the square root of 4. There's nothing we can do about the 2, so that goes there. Now we can actually multiply 2 with 2, which is going to give us 4 root 2 as our final answer. Okay, whereas if you just use 16 right away, you can see this then becomes square root of 16 times 2. We know that square root of 16 is 4, and there's 4 root 2. Okay, it gives you the same result. Okay, so it does not matter. Okay, it doesn't matter. You could use a smaller factor, that's fine. It's just not going to take you extra steps. Okay, this case here, cube root of 56, this is simply cube root of 8 times 7. We do know that the cube root of 8 is a 2, so then the answer is going to be 2 times cube root of 7. Okay. Finally, okay, the third example here, there's a fraction now. I don't know if you know how to deal with it, so I'm going to show you. Okay, what we can do is we can just really look at them separately. Okay, so we have the square root of 27 and the square root of 28. So what we can do is, again, look for the perfect square factors. 27 is equal to 9 times 3, so we can do this. 28 is 4 times 7, so we can do this. Okay, and after that, what we can do is we can still split. Now, instead of multiplication, right, we're going to split the division, I suppose. So I'm going to actually take out 9 over 4, and I'm going to keep the multiplication remains as the multiplication, 3 over 7 inside the radical. Okay, so as the radicand. Now, here we have the square root of 9 over 4. So what we can do is we can actually square root them, the numerator and denominator, separately. Okay, square root of 9 is a 3, square root of 4 is a 2. So that's how we end up with 3 over 2. And there's absolutely nothing we can do about the square root of 3 over 7. So then we just leave it as it is. And that's our final answer. Okay, so if it's a fraction, you just proceed as how we did it in the previous examples. But we can actually take out the fractions outside as well. Okay, so that's the only difference. Okay, all right, so that's the first method by using perfect powers. This is a good method if the numbers are not super big. Okay, I mean, if you go to the next page, you can see, so we now have some bigger numbers. It's sometimes more challenging to look for factors of 648. That's also a perfect square. So I'm going to show you a different method, okay, and this is using prime factors. Okay, prime factorization, which you learn in math 8 for sure. Okay, factor tree. Okay, so I'm going to show you. Okay, so 60, we're going to do factor tree for 60. 60 is equal to, let's just go 2 times 30. Okay, and then 30 is 6 times 5. 6 is equal to 2 times 3. Okay, so what I'm going to do is 60 is the same as 2 times 2 times 3 times 5, right? So at the end of the branches, those are the factors of 60. So square root of 60 is equal to 2 times 2 times 3 times 5. Square root of that. Now from here, because these two are the same numbers, okay, so what happened then is when you square root of 2 times 2, it actually just ends up with a 2, right? When you square root 2 times 2, because they are the same numbers, right? So when you square root the same numbers multiplied by itself, it's just that number itself, okay? However, we still have the 3 and 5 remaining inside the radical, so and there's nothing we can do, so 3 times 5 is just 15, and that's the answer. Okay, square root of 60 is 2 root 15. Okay, now let me show you an example with a bigger number here, 648. Okay, again, we need to do prime factorization for this. 3 is gonna work. Okay, so that's 216. If you're looking for some tricks, divisibility rules, I don't know if you remember for 2s. For 2 is easy. As long as an even number, 2 will work. 5 is easy. Is also easy because as long as the number ends with a 5 or 0, then 5 will be divisible. 3 is a number, is actually also easy to check. So I suggest you to learn this, I guess. What you do is you add up these 3 digits. So 6 plus 4 plus 8, which is 18. And 18 definitely is a multiple of 3. So 3 is a divisor of 18. That means 3 is going to work. For example, here 216, 2 plus 1 plus 6, right? You add up the digits. 2 plus 1 is 3, 3 plus 6 is 9. So 9 is a multiple of 3. And therefore 3 will go into 216 evenly, okay? This is going to be 72. Oops, 72 and 3, okay? Now 72, we know that's 8 times 9. And 9 is simply 3 times 3. So these are the end of branches. I'm going to circle them. 8 is 4 times 2. And 4 is 2 times 2. All right. So we have the cube root of 648. And this is the same thing as how many 2's do we have? We have 1, 2, 3 2, so 2 times 2 times 2. We have 4 3's, 1 times 3, 2, 3, 4. Okay. Now, so what's different when we do cube root compared to square root is in the square root we group 2 of the same numbers. Here it's a cube root, so we group 3 of the same numbers. So we have 3 2's, we have 3 3's, and we still have 1 extra 3 remaining inside. So what that means is when we cube root 2 times 2 times 2, the end result is just going to be a 2. When we cube root 3 times 3 times 3, the end result is just going to be a 3. And there is a 3 remaining inside the radical, and there's absolutely nothing we can do about it. So once we have this, we can simply multiply the 2 and the 3, we get 6. And so our final answer is 6 cube root of 3, and that's it. Okay, so there are 2 examples for you to practice. Okay, so give it a try. Okay, so I'm assuming you finished it. I'll do it quickly here. 72 is equal to 8 times 9, which is 2 times 4, and that's 2 times 2. 3 is 9. Sorry, 9 is 3 times 3. So we have 2 times 2 times 2 times 3 times 3. And again, we have 2 2's, we have 2 3's. So that is going to give us 2 times 3. We have a 2 remaining, and 2 times 3 is 6. So the answer is 6 root 2. For 432, let's see, 4 plus 3 is 7, 7 plus 2 is 9, so 3 is going to work. Okay, so 432 is going to be 3 times 144. 144, yes. And 144, again, 1 plus 4 is 9, so we can actually divide by 3 again. This is 48. 48 is 8 times 6. That's 2 times 3. This is 4 times 2, so that's 2 times 2. I'm going to, again, circle all the numbers at the end of the branches so I don't forget. So we have how many 2's? 1, 2, 3, 4. 4 2's. 1, 2, 3, 4, and 3 3's. 1, 2, 3. Okay, so again, we're going to put them in group of 3. Okay, so 3 2's, 3 3's. So this is going to be 2 times 3 times the cube root of 2, which is 6 cube root of 2. Okay? Hopefully you got those 2 right. And that's how you simplify radicals. Okay, or convert entire radicals to mixed radicals. This, oh yeah, I guess I forgot to mention, this is what we call a mixed radical. Mixed radical means it composes of a whole number and a radical. Whereas this, let me see here, I'm going to do it here. This is called an entire radical because it has nothing else except just one single radical, right? That's an entire radical. This is also an entire radical. Okay, these are what we call mixed radicals. Okay, again, mixed radical means it has a number outside and there's a radical. And entire radical is just one single radical, nothing else. Okay, so now we're going to go opposite. Okay, we're going to go backwards. We're going to write mixed radicals as entire radicals. Okay, so here, notice this is a mixed radical because it has a 2 outside of the radical, and we have a radical still. Okay, so this is a mixed radical. We are going to convert this into entire radical. So basically what we do is we do the opposite. We go backwards, right? I mean, think about this. How did we get the 2 to be outside? Where does this 2 came from? Well, 2 really came from the square root of 4, right? And the root 7, well, that remains as root 7. And remember, when we have 2 radicals multiplied together, we could actually go back and put it into one single radical, right? Like that, 4 times 7. And therefore, this is square root of 28. And there you go, that's it, okay? It's actually quite easy. Similarly with the cube roots, okay? So we have the 5 times cube root of 3. So again, think about where we got this 5 from. This really came from the cube root of 5 times 5 times 5, right? That's how we got the 5 to be outside. Because we have 3 5's in the cube roots, okay? And we still have the cube root of 3. Okay, and now you just need to multiply all these four numbers together. So the cube root of 5 times 5 times 5 times 3, that's 125 times 3, so I believe it's 375. So this is the cube root of 375. Okay. All right, there are three numbers for you, so three practice questions for you, so give it a try. Okay, so this one is simply going to be square root of 49 times 2, which is square root of 98. The second one, this is going to be the cube root of 4 times 4 times 4 times 2, which is 128. Right? So it's the cube root of 128. Okay, now here's an example of a mixed radical with fractions. So similarly, okay, like what we did before, where does this 2 over 3 came from? It really came from the square root of 2 times 2 over 3 times 3. Okay, and we just have another 5 there. Okay, so then this is going to be, hopefully you remember how to multiply fractions. When you multiply by the whole numbers, really it goes to the numerator. Okay, so now if you expand this, this is 4 times 5 is 20 divided by 9. And that will be the answer. Okay, hopefully it's not too difficult for you. Okay, last thing we need to talk about today is some definitions. Okay, so rational numbers and irrational numbers. So I'll give you a formal definition of a rational number, and then I'll give you a everybody understands language to explain what a rational number is. Okay, so rational number by definition is a number that can be written as a fraction m divided by n, where m and n are both integers. And of course, n cannot equal to 0. Right? We cannot divide by 0. Okay, so any number that can be written as a fraction m divided by n, where m and n are both integers and n cannot equal to 0, are what we call rational numbers. Okay, so you still might feel like, oh, okay, so what exactly it is, right? Like, I'm still not quite understand what are you talking about. Okay. If I'm converting this to decimals, that might be easier for you to understand, okay? But that's the formal definition. If you're thinking about decimals, okay, rational numbers are any decimals that terminates or repeats, okay? So for example, 4.1, that is a rational number because it terminates at 0.1. There's nothing else after that, okay? 0.3333 repeating. This is a rational number because it repeats. Because, I mean, if you think about it, 0.333 repeating is really just 1 over 3, right? Again, that can be written as a fraction. 4.1 can be written as a fraction. This is simply 41 out of 10, right? That's why they are rational numbers, because they can actually be written as a fraction, m over n, where m and n are both integers. Okay? So then you might think, okay, well then in that case, what's not a rational number then, right? So here is the definition of irrational number. The definition of irrational number is not a rational number. I'm not even joking. That's the definition of it, not a rational number. Okay? Within real number system, of course, I should mention about that. So not a rational number. So then Mr. H, what are you talking about? What's not a rational number then? Okay? So not a rational number, pi, because that if you write pi as a decimal, it's 3.14159, blah, 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 blah. It does not end, right? It does not terminate, and it does not repeat. And therefore, it is irrational. Another example, and really, this is the one that ties into today's lesson, square roots, okay? Square root of 3 is not a rational number. It's irrational, okay? It is irrational. Because if you put that into a calculator, it does not terminate, it does not end, it just continues without patterns. Square root of 5, square root of 2. However, not all radicals are irrational numbers, right? I mean, if you think about this, square root of 4, this is irrational. This is rational, right? Because root 4 is simply 2. Okay, so be careful. Not all radicals are irrational. Obviously, we can do more examples with the cube roots. To 5, right? Whatever, doesn't matter. 4th root of 10. These are all irrationals. Okay. All right. That's the lesson for today. Give you a heads up. Notice how I did not use calculators at all for today's lesson. So you would be expected to do your homework questions without calculators as well. And so is your test. Okay. So do your best to practice, doing your homework questions without calculator. Okay. All right. That's it for today. Enjoy your homework and then have a good weekend.